All right, so let's get started. So today we'll talk about some advanced research topics related to the things you learn in lecture 2 and lecture 3. But because those are all advanced research topics, so actually most of the things that we talk today will not be in your final exams. Okay, and for the last 30 minutes for today's lecture, we'll announce our second hands-on, and then there are some instructions, and then TA will take over for that part. Okay, so before we get started into the details about the research topic, let me give you a very brief overview of the four main researches that we will talk about, and they share the same big story. So actually, as you already see in the slides, like the data growth from 2012 is faster than Moore's law. So that means like if you are going to store most of the data related to the applications in your systems, then you need to increase a lot of price to buy more DRAM, for example. Okay, but if you don't want to buy too much of DRAM because DRAM is usually expensive and then it consumes a lot of energy. So another way you can do is to have more storage device to have the to become some memory backup. And the thing is like if you are facing like if you are going to deploy a big data applications, and usually you will find the storage and memory to compute, there will be a lot of data movements there because a big data application usually do not have that specific access patterns, just like general application, like they have so obvious spatial or temporal locality there. So usually there are data movements between memory storage and memory and compute. Okay, so today we'll focus on the storage to memory part. So we're going to think about like what kind of designs can help to alleviate or like how to remove the movement between the storage and memory. So the way to remove it actually is to increase the size of the main memory. But we say like this is a way for hybrid main memory. The reason is actually we are trying to increase the main memory by using some slower memory device. Usually we're using something like storage device. So there are two general ways to increase the main memory. The first one is the hardware control memory extension. So hardware control memory extension, you can think about just like maybe in your DRAM, usually in your memory, there are not only DRAM chips, but also there are some flash memory chips. So flash memory, just like your SSD, they're using flash memory. And usually this is a device. So inside the device, there is a controller. So the DIMM controller, you can think about just like a tiny or embedded CPU. So this DIMM controller is going to navigate the request. For example, if the CPU is going to access the data from the slow memory or like from the NAND flash memory, then the DIMM controller will help to check about, okay, where is the data and what is the address, then getting the data, then return to the CPU. So you can think about this one is a device. So the thing is, because this is a memory device, so when the CPU is going to access the data in a slow memory, usually there will be no interrupt. I mean, there will be no operating system can enter, okay? Because this is a device, just like DRAM. So when CPU accesses DRAM, CPU will not execute operating system. CPU will directly load store the DRAM. So this is the same concept. Even there is some slow device inside, the same things, CPU will still be waiting here. Okay, so we have another architecture. It's called OS control memory extension. So this is quite intuitive because you already use these kind of things in most of your systems. The thing is called swap. Just like if you have a storage device and you open the swap functions, then the operating system swap function can help to manage the data in the storage device to make the storage device runs like the extension of the main memory. Okay, so the controller is the operating systems. So left-hand side, the controller is one spatial, you can think about one spatial CPU. And then the right-hand side, just like you use the operating system to control the store device part to make it work like the main memory. Okay. So we have 4 topics. Then first one, let's start from the hardware control memory extension first. Okay. So actually, in 2016, around 2016, Intel and HP, they announced their hybrid memory device. So at that time, the device called like NVDIMM. So inside NVDIMM, there are 3 main parts. The first part is the memory chips, the fast memory chips. And the fast memory chips usually is kind of DRAM. And then there is another memory chip is slow memory chips. So slow memory chips are usually used from the NAND flash. Okay, so having DRAM and NAND flash together in one device, you can get a good thing is the price will not be so high and you can get a lot of memory space, right? You can think about if one day it is possible to making SSD and DRAM together, then SSD is cheap and SSD can provide larger space, okay? But the thing is because NAND flash or like SSD is slow, so we call them slow memory. And if you still remember, 2 weeks ago, we talked about like the NAND flash or like SSD, the latency is kind of 10 to 100 times slower than main memory. So actually here, slow is really super slow. And then the DIMM controller here is going to navigate the data relocation or like to navigate the data movement between fast and slow memory inside this NVDIMM. Okay, so traditionally, we only have the DRAM as our main memory. And at that time, when CPU is going to access the data from the memory, we call it memory wall, right? The reason is CPU loads all the data from DRAM, but actually DRAM needs to return for like 50 nanoseconds to return the data to the CPU. But CPU, if you are using a 3 GHz CPU, then the response time or like the time to access the instructions will be 0.3 nanoseconds. So CPU is super fast than the DRAM. So when the data is in the DRAM, CPU needs to wait for a relative long time, like 10 to 100 times slower than CPU itself. So we call it memory wall. But now with this NVDIMM device, we call it great memory wall because when CPU is going to wait for the like NAND flash memory, CPU should wait for around like 1 microseconds or like several hundred of nanoseconds. So it is 1,000 times lower than memory wall. Okay, so our idea is about how to solve these questions. Actually, there are 2 parts of this solution. First of all, we need a thing called the store-aware process state diagram. So coming back to our architecture, the reason like CPU should wait for a super long time is because NVDIMM is a memory device. So in current architecture, when CPU is going to access a memory device, CPU will be busy waiting there, right? Because usually memory is so fast. So CPU usually don't need to wait too much of time. But now, this kind of new memory device, there are some slower device chips called NAND flash chip inside. So CPU need to wait for a relatively long time. So the first thing we are going to do is to let CPU know, hey, actually CPU is now waiting for a slower memory device. And then CPU can like interrupt itself to jump into the operating system kernel to run some like functions to help on this. Sorry. Okay. So first of all, let's talk about how to let the CPU know CPU is now waiting for a super slow device. So if you still remember, this is our process state diagram. I mean the white circle parts, and we include a new state called exception state. So we add a new process state code exception to handle the timeout exceptions issued by the CPU. Actually, we have another kind of assumption is for the new CPU, it is possible to include a timer. So the timer is ticked when every time CPU is going to access the memory. Okay, so when timer takes over like 60 nanoseconds or like 70 nanoseconds, the timer will trigger interrupt to interrupt the CPU itself, to interrupt the CPU core. So when the timer interrupts the CPU core, CPU can jump into this exception state. So CPU can decide, is it going to keep running or it is going to do the waiting things. So the waiting thing, just as you already know, just like we will do some DMA setting, and then we will run the context switch to switch in other process and then to switch out the current process. Okay, so the goal is to explore the idle CPU resource to provide process with hints for marking and relocation. So actually, patch marking here you can think about is to prepare to let the operating system to do some prefetching, because we need to send some hints to let the operating system know what kind of data we are going to do the prefetch. Okay. Okay. So our second strategy will be like patch semantic aware strategy. So this strategy is going to bridge the semantic between the CPU and MVDIM. So there are several steps here. And then the first step is the most important step is called patch marking. So for patch marking, it's about CPU will sense the predicted physical address into the MVDIM. Okay, so as you already know, current CPU, we should translate the virtual address to the physical address before CPU access the memory, because for current programs, they are written on the virtual address. So CPU should first do the translation to make it from virtual address to physical address. So after getting the physical address, CPU can send it into the DIMM controller here. So the reason is for the DIMM controller, actually this controller is inside the MVDIMM device. It's inside the device. So this controller doesn't have any information about process or like patch table, those kind of things, because this is only the CPU running in one memory device. The CPU outside the MVDIMM or like the main CPU, as it has more permissions to access like patch table or process information or like those text structure things. So CPU outside the MVDIMM can help to collect those kind of address informations and then send them into the DIMM controller to do the further prefetching things. So patch relocation is quite simple, just like after getting the information from outside CPU, the DIMM controller can know which physical address we are going to do the relocation. Just like we're going to move the data from flash memory to the DRAM, and then to move some data from DRAM back to the flash memory. Okay. But the thing is about, okay, we have our framework. I mean, CPU can interrupt itself by using a timer, and CPU can jump into the process state diagram, and CPU is possible to do some prefetching, right? But what kind of data can be prefetched? How to know what kind of data will be accessed later? So we do some experiments on several popular applications. So this Radiosity, TensorFlow, Deep, WAF, Blender, and Caffe. Some of them are from the high performance computing applications, and some are like TensorFlow, just like running some image recognition things. So the conclusion is like actually we found the process typically shows strong spatial locality on the virtual address space. So if you look at the figure below, like the x-axis are those applications, and let's first focus on the left-hand side. So left-hand side shows two different memory access, non-continuous access and continuous access. So those access are collected from the point of view of the virtual address space. So we can see actually more than more than 40% of the memory access, they show continuous access. So only few of them, they are very close to 40, but like Radiosity, TensorFlow, or Dedupe, like those kind of file-based application usually shows more than 40%. There are some of them can be 80%. So there do have some locality on the virtual address space. And we do a deep dive into, so what kind of locality it is. And then we do some analysis on the continuous access. So we break down the continuous access into two things. One is called the forward continuous. Another is called the backward continuous. So backward continuous, you can think about just like now CPU is now accessing one virtual address. And then backward continuous means those addresses, they are smaller than this virtual address. It is called backward. So larger is called forward. So you can see for some application like TensorFlow, Cafe, and Blender, actually they show some backward continuous access pattern. So I think forward for you guys will be quite intuitive because program usually go, move forward, right? But backward, the reason we have backward memory access is because for some image related applications, for example, if you are going to do the median filter, if you are going to use a kernel to do some convolutional neural network, those kind of things, usually you are going to access the memory around the target virtual memory address. So it is possible to access some address smaller than the current memory. Okay. So especially for those especially for those applications that have this kind of square-like mask, it is possible to access the backward things. Okay. So now we know for some applications they show backward continuous, but for some actually there is no backward. Most of them they are forward continuous. So the thing is about how to provide this kind of information to do the prefetching. So we design a thing called patch on patch. So patch on patch is about because currently patch is 4 kilobytes, and we say there are forward and backward. So we try to assemble several patches together. So in this case, actually we assemble like 64 kilobytes. So we assemble 16 patches together to be a larger unit. So you can think about patch on patch is a little bit like huge patch, but actually for huge patch, you need to define a specific size. For example, huge patch only support like 2 megabytes or 1 gigabyte because of the patch table design. And now we are going to design a new smaller unit called patch on patch unit. It is also the fixed length, and it is a continuous on the virtual address space. So the good thing is about if we have a patch on patch unit and we have their ID and patch start and patch end, so patch start and patch end will include 16 patches here, and 16 patches there are continuous on the virtual address space. So in this case, actually, if there are some keys between these 16 patches, then we will prefetch all the 16 patches to the DRAM from the flash memory. Okay, so this patch on patch list will be large if the application use a lot of memory. So we can keep part of this patch on patch unit list in the CPU cache. In this case, when CPU is going to book the patch table, CPU can also quickly get the patch on patch unit information from the CPU cache. Then CPU can quickly identify which patch or like those patches which will be accessed later can be moved beforehand. Okay, so this is the way like how to do the prefetching and how to use this kind of virtual address information. And for evaluation, I will skip it. I think it's not that important because usually it will be effective, otherwise you will not be published. Okay, so the first topic we are talking about the hardware control memory extension. And for the second to the last one, we will talk about how to do the memory extension from operating system aspect. So the second one we will talk about when there are some very fast storage device, how the operating system be rethinked. So operating system basis memory extension will use swap to do the memory extension. So you can look at the figure, like here will be an ultra low latency storage device. And for inside the storage device, part of it will be configured as a swap area. So the data can be moved from the swap area to the memory, or from the memory into the swap area. Okay. So let me briefly differentiate what is the difference between like swap and the like patch cache thing. Because if you know about Linux, there is a thing called patch cache. Is when you access a file in the storage device, actually system will cache them in the memory. So actually there are two paths for the process to access the data inside a storage device. The first one is when MMU reads patch fault, because the data is not in the memory. So usually the data is in the storage device. So we are going to get the data back from the storage device. Then when MMU reads a patch fault, CPU will jump into the kernel and the CPU will run the patch fault handler. And there are three main steps usually inside the patch fault handler. First of all, we are going to check where is the fault. So the fault area checking, and then we are going to do the patch swapping. So patch swapping is more like the operating system will set up the DMA to move the data from the storage device back to the memory. But they're just kind of a DMA setting, not really a data movement, because data movement takes a lot of time. So after configuring the DMA, CPU will do the context switch to another process. So this path is the thing you learn, and swap, they're using this path. And usually we call it this place is like the process IO. And there is another path is called the file IO. So file IO is just like how to access the data in a file system. So for file IO, when the program is executing in the CPU, usually there are some system call be triggered. For example, if you're writing a C library, you use a fread or fwrite, then CPU will call the rewrite system call. So for a rewrite system call, there are three main steps here. The first one, CPU will check the patch cache to look about if there is a data cache in the patch cache. So if there is, then CPU will directly get the data in the patch cache. And because the patch cache is in the DRAM, so CPU can get it super fast. But if the data is not in the patch cache, that means the data is in the storage device, I mean the file data. So CPU will run the file system and then to check where is the data. Then after that, CPU will once again do the context switch, because switching the file data from storage to memory, it takes also a lot of time. Okay, so today we'll focus on this one. The swapping is on the left-hand side part. So here are just kind of a lot of device things. So actually it's just about to let you know, hey, our peripheral buses, it scales from 600 megabyte to 4 gigabyte of the throughput. So it is good things. And also our latency also decreased a lot. So traditionally, if you focus on the emitting part, actually the emitting part, the fastest speed is 15 nanoseconds, just like data in the DRAM. But the slowest cache will be the data in the NAND flash, so it will be 15 microseconds. So in the year around like 2018 or 2019, Intel and Samsung announced their ultra low latency storage device, because they are ultra low latency. So the Optane SSD can achieve like 6 microseconds, and Samsung Z-NAND will be like 3 microseconds. Okay, so why those devices are so important? I mean, why those throughput and latency are so important? So the reason is, come to think about, if your device can support a super high throughput, that means you can move a lot of data at the same time. You can have high parallelism to move them. And if you have a super low latency device, that means you can move one data in a super short time. So they both are a little bit similar, but they have different effectiveness. Okay, so if our storage device now can offer like 5 to 10 microseconds of the IO completion time, then how about context switch? Because if you look at this figure again, actually, no matter you are doing a process IO or file IO, the last step is context switch, because in the traditional operating system, storage device is super slow. So when the data is in a storage device and CPU needs the data, CPU will not busy waiting for the data. CPU will do context switch, and then to let the data moving becomes asynchronous. Okay. But the thing is about actually doing the context switch, it takes about 5 to 10 microseconds. So the time is very close to getting the data from an ultra low latency storage device. Because ultra low latency storage device, it range between 1 to 10 microseconds. And for Samsung VNAND, it's 3 microseconds usually. Okay. So doing context switch is not always a good choice, because in this case, if you are going to get a data from 3 microsecond device, but you need to wait for the 5 to 10 microseconds context switch, then why not just let the CPU busy waiting for the storage device? Why not just remove the context switch? Okay, so to serve this super fast storage device, just like Intel and IBM, they're supposed to use the synchronous I/O. So synchronous I/O is quite easy, just like to let CPU busy waiting for the device I/O. So for example, if the data is in the storage device, and if the CPU needs the data, but because we know this is the ultra low latency storage device, so CPU just busy waiting there. CPU will not do any context switch. CPU just wait here, wait for the I/O completion, and CPU can keep moving. Okay, so we do some evaluation to let you know actually this makes sense. Okay, so the x-axis here is in both figures, they are showing different patch size. So we configure if the operating system using the 4 kilobyte and 2 megabyte, and there are two kind of dummy configuration. So 32 kilobyte and 256 kilobytes, we're using a simulation to simulate using these two different patch size. So actually, two figures are showing very similar things. The only difference is about how many processes they are running simultaneously. So left-hand side, we run 3 processes at the same time, and right-hand side, we run 6 processes at the same time. So the key thing is about the configuration. So there are we evaluate on 2 different kind of SSD. One is 3 microseconds ultra low latency SSD, and the other will be the 10 microseconds SSD. And then we let the operating system to support 2 different modes. One is called asynchronous mode. So asynchronous mode, you can think about just operating system will run the context switch. And the synchronous I/O mode here is about to do the busy waiting, no context switch. Okay. And in our system, we have do the evaluation on our system, and the testing result is about context switch latency is around 7 microseconds. So the y-axis in both figures, they're showing the total CPU wasting time. So CPU wasting time means about CPU cannot run the process progress. It means like when CPU needs to do context switch, or like CPU busy waiting for the I/O, those are called CPU wasting time. So lower CPU wasting time is better. That means CPU can fully dedicated for running a process progress, not for those kind of operating system context switch or like the I/O. So you can see for both figures, they show like if the patch size is more than 32 kilobyte, no matter you are choosing 32 kilobyte or 4 kilobyte. For those kind of ultra low latency device, like 3 microsecond one, and they are using the synchronous. So the solid line here, the red solid line here, we can get the best performance. Okay, so no matter you're running 3 or 6 processes, they are showing the same trend. So we draw a first conclusion is if now most of the I/O are in the small I/O size, or like if you are using the smaller patch size, then if you have a super fast storage device, then you should go for a synchronous I/O. Okay. But the thing changed when you change from a 32 kilobyte to a 256 kilobyte, or even the 2 megabyte patch systems. So this is going to show you like when the I/O size grows to more than 32 kilobyte, then this is called the large I/O systems. So for these large I/O systems, asynchronous I/O or running context switch is still a better choice. The reason is about if you can leverage this kind of large I/O, for example, the 256 kilobyte or 2 megabyte, if you can move those data at the same time, then you can enjoy the SSD parallelism. So you can see like for 32 kilobyte, if you choose the synchronous I/O, and for 256 kilobyte, if you choose a synchronous I/O, actually the time is very similar to each one. Okay, and the reason is about 256 kilobyte. Actually, when you are going to move to 256 kilobyte, actually you will spend more times than 32 kilobyte because you move more data, right? But the thing is about 256 kilobyte, it means like you need to move 64 pages at the same time. And 64 pages means if you can have an accurate guess about what pages you are going to move, then you can achieve a good prevention. So if you can move like 64 pages at the same time and beforehand, then you can reduce a lot of page faults. So this is the reason why when you increase the page size, in some cases it helps. So in some cases, actually huge page is a good configuration. If you can make sure the assets show very strong spatial locality. Okay. Okay. So the thing is about like if the page size grows more than 256 kilobyte, if you in this figure actually up to 2 megabyte, no matter using which configurations. I mean, if even you are using the ultra low latency device or like using a general device, actually all the CPU wasting time grows. So what is the reason? So the reason is about we make a deeper evaluation on each pages. So we find like actually when we are using a huge page, like using a 2 megabyte, so in most cases, huge page show low utilization. So low utilization means like actually there are only lower than 5% of the data inside the 2 megabyte huge page will be really accessed. Okay, so if you look at most of the application here, from Blender to Cafe, most of the applications, if they use huge page, then for most huge pages, they only show lower than 5% of the usage. So here's an exception, it's called dedupe. So dedupe is a file-based application, just like dedupe usually read out the whole file, the image file of a video file from the storage device. So dedupe get a super high utilization if we use the huge page. Okay, but rest of them, the utilization is low. So this low utilization will increase the CPU wasting time because low utilization means like you usually get a miss when you are going to move these 2 megabyte data together. Okay, so based on those experiments, we can have some takeaways here. So first of all, if your systems are using the smaller page size, 4 kilobyte or like a little bit larger than 4 kilobyte, so we should enjoy the ultra low patch promotion speed without the intervention of content switch. Just like we don't need content switch, we just busy waiting there. And then if you are confident to able to move more pages, for example, 256 kilobyte of pages, that means like if you think you can guess the next 64 pages, which one will be accessed next. If you can predict the future patch, if you can predict the future patch access, then you can avoid future patch faults by using the asynchronous I/O. That means like using context switch, but because you move more data, and then you know those data will be accessed in the near future, so it will be also helpful. Okay. So the thing is about how to design a systematic solution to enjoy both strengths. Okay, so here are several challenges here. First of all is actually in current operating system, if you are using paging, either you pick for the 2 megabyte or 1 gigabyte, or go for the regular 4 kilobyte pages. So you cannot mix the two pages together usually. So needless to say, you cannot choose a 32 kilobyte or 256 kilobyte if you use an Intel CPU. So the thing is, how to break this constraint? I mean, how to let a system can support this kind of 32 kilobyte is one critical thing that we are going to achieve. Okay, so actually this work, we modified the huge patch design inside the Linux. So last time we talked about huge patch design. It means like you need to move like 2 megabyte or 1 gigabyte of data continuous together from the storage to the memory. Okay. So actually we have several designs here. First of all is about shadow patch promotion. So the shadow patch promotion is going to avoid unnecessary data movement as promoting a huge patch. So huge patch promotion is about, if you are going to do the huge patch promotion, you need to read out a lot of patches, 4KB patches from store device, and then to group them inside the memory to make them continuous on the physical address. So it takes a lot of time, and we are trying to alleviate this overhead. And the second one is, just as I mentioned, how to support this kind of like variable size patches. Then how to design what kind of patches we are going to do. So we have a variable size patch prefetcher. Okay, so first of all, we're going to introduce about the shadow patch promotion. So for the shadow patch promotion, in the physical address space, because we have DRAM and then we have the UL device as our swap area, right? So now, if we have a shadow huge patch in the memory, so actually huge patch is like 2 megabyte, but this is too huge. So let me simplify this example. So this red part is a huge patch. Like we said, it is 2 megabyte. And because 2 megabyte is too huge, so actually we have a new design called shadow huge patch, just like a part of the huge patch. So this is a shadow huge patch. So if, for example, if the huge patch is 2 megabyte, then if we set our shadow huge patch to like 64 kilobyte, then this area, this 16 continuous patches area will be configured as one shadow huge patch. So for this case, if there are two different things, one is shadow patch, the light orange, and there are dark orange. So dark orange or orange means like the data is already in the DRAM, but the light orange means the data is in the storage device. So if we are going to create this shadow huge patch, traditionally we need to move the data from UL device into this light orange area. Okay. Okay, but the thing is about, if we are going to move the data from UL device to the memory to configure a larger patch, for example, a 256 kilobyte patch, then it takes a lot of time because moving data from store device to memory will be time consuming. So we will defer the data movement. What I mean defer is about, you can think about just like copy and write. I mean, we don't copy the data when we are going to create this shadow huge patch. We will just mark them in the patch table to say like, hey, actually, here, these 4 patches are belonging to one shadow huge patch. But actually, the last 2 light orange part, actually, the data is still in the device. Okay. So how to realize these kind of things? The first is about, if the data is in the memory, then we will promote unconstruction. It means like, if we are going to construct this area, then we will move the data from DRAM from some locations to this location. And because those data, they are all on the memory, or they are all on the DRAM, so this movement will be super fast. So we can do it immediately when we are going to create a larger patch, I mean, larger than 4 kilobytes. But for those data that are in the store device, we don't do the data movement at the time the shadow huge patch is created. because it takes too much of time. So we will promote it on demand. On demand means like when the data is really accessed by the process, we'll do the data movement. Otherwise, we will not really move the data. Okay, because if you still remember, we do the utilization testing. We show you like actually when we are using a large page size like 2 megabyte, like more than 95% of the huge page, the data will not be accessed. So only 5% of data will be accessed. In this case, why not just delay to move them when they are being accessed? Okay. But the problem is, so if CPU access without any check-in and CPU directly access this area, and because DRAM is a memory, so when CPU access DRAM, CPU will directly load and store. But if there is no any extra check-in, CPU will directly read out the data from this shadow pages. But actually, the data inside is wrong because the data should be in the store device. Okay, so there will be an error here if the CPU directly access it. So actually, we briefly modify the TOB inside the CPU. Like we included new things called present map. So the map structure is more like we will give this shadow patch. For the shadow patch, we'll give each 4 kilobyte area will give 1 bit. So this 1 bit, 1 bit, 1 bit, and 1 bit. So we have 4 bits here. So these 4 bits can identify which location there is not ready. For example, the last 2 shadow pages, actually the data is still in the store device. So the bit will not be set. So for this power support, CPU can find which 4 KB patch is still in the store device. So CPU can trigger the operating system to move it from the UO device first. And this is the reason why we say we will promote it on demand. Because if the CPU is going to access this area, CPU will first check the present map to check about if the data is in the memory or not. So if the data is in the memory, then we don't do anything. But if the data is not in the memory, then we'll promote it on demand to promote from the store device. Okay. Okay. So, but we have another issues here. So the issues is like this. If we now this is a 256 kilobyte patch. 256 kilobyte patch means like this is about 64 4 kilobyte area, right? But if most of the area, the data is still in the store device, then if there is one place that is accessed now, and CPU is designed to move the data from the store device to the memory, and we say if it is possible, if you can predict which patch will be accessed later, and you can move more patches, then it will be more cost effective, right? So we need some way to do the prevention. We need some way to do the prevention about what kind of data will be accessed first. Okay, so actually the key idea is about like we maintain several lists about how to do the prevention. So actually, if there is, for example, if this area is accessed one times, then we will be moved into this pyramid. And if this area accessed twice, for example, there's the second access is here, then we will promote this shadow huge patch to the higher level. So you can think about actually, if the shadow huge patch is in the first level, then we will not do any prevention because it means like this is a code. This is still a code kind of shadow huge patch. But when this shadow huge patch being accessed more than 2 or even 3 times, we will do the prevention more aggressively. Okay, so you can see like if we access the shadow huge patch several times, then we will promote more patches via the asynchronous I/O. But if the shadow huge patch only be accessed 1 or 2 times, then maybe this is just about lucky. So we will not do the more patches promotion. We will only promote fewer patches, usually like 2 or 4 patches. Okay, so this is a way to decide about how many patches we are going to move at the same time. Okay, so this is the idea about how to make the system support like the patch size between 4 kilobyte and 2 megabyte, and to leverage the synchronous and asynchronous I/O. Okay, so let's move on to the third work. So the third work, we dive into the synchronous I/O part, because we say about like, hey, actually, if you have a super fast storage device, and then if your I/O is 4 kilobyte to 32 kilobyte, and usually most of the system now they're using 4 kilobyte, so it means like synchronous I/O maybe in some days will become a mainstream. So our next question is about, so what will happen if current system now they're using the synchronous I/O? Okay, so the thing is about the scheduling. So come to think about when we are using the currently when we are using a asynchronous patch fault handling, it means like when there is a patch fault, we will do the reschedule, right? Otherwise, we will wait for a timeout. So if there are several processes here, there are T1 to T4. So T1 and T2, they are memory intensive process, and T3 and T4, they are compute intensive. So because T1 and T2 is memory intensive, so usually the data will be stored in a storage device. Then when CPU is going to access this data, CPU will trigger patch fault, and then will trigger context switch. So for the asynchronous patch fault handling, T1 and T2 will be switched off very frequent. But T3 and T4, because they are non-memory intensive, they are compute intensive. So usually they will be rescheduled only when timeout. Okay, so if those processes, they are in the same priority, then T3 and T4 can use up more CPU times than T1 and T2. Okay, so this is asynchronous patch fault handling now happens. So when we move to the synchronous patch fault handling, the things change because the rescheduling period will be only timeout because there is no context switch during the patch fault, right? Because we are using synchronous patch fault handling, so if there is a patch fault, then CPU will be busy waiting there. So there is no context switch. And in this case, all the process can use up their own timestamp. So because T1, T2, T3, and T4, maybe they are in the same priority, so they can use up all their time slice. Okay. So this is the synchronous patch fault handling. Okay. And the thing is about let's use only single core for an example. Just like for scheduling T1, actually after T1 is finished, T1 should wait for a -1 task before the next time it can be accessed because it is synchronous patch fault handling. So there is no context switch between them. Okay, they only need to wait this T2, T3, T4, and the three of them becomes timeout, then T1 can be executed again. Okay, so what's the problem? I mean, what's the problem when you are using this synchronous patch fault handling? So things we observe is a things called working set contention. Okay, so working set contention looks like this. If there are 4 processes, P1, P2, P3, and P4, and they are in the same priority now. So now when the CPU is executing P1, so you can think about like the working set related to P1 will be moved into DRAM, right? So the reason is about when each time it triggers a patch fault, then the data will be moved from storage to DRAM, but we will not trigger context switch. So P1 will be executed only, will be stopped only when the time slice is exhausted. So the same things, P2 do the same things. So now inside the DRAM, there are P1, P2's working set, and then it's P3. Okay. But the thing is, when P4 is running, because there is no room for DRAM, so part of the P1 and P2's working set will be evicted to the ultra low latency device. And now, if once again, P1 is not executing now, then because inside DRAM, there is no P1 related patches. So P1 will face a lot of patch faults. So P1 should wait for a super long I/O completion time to wait for the synchronous I/O. And the reason is because the working set, P1's working sets, they are kicked out by P4. Okay. So one moment. Okay. So let's take a 10 and come back later.